Welcome to the Rori Academy YouTube channel, where we present information that helps you improve your understanding and knowledge about power electronics technology and its emerging applications. Today, we will focus on the commercially available Volkswagen ID series battery electric vehicle models. Today, we will focus on the power electronics technology associated with Tesla Model 3, Infineon IGBT and the inverter stage of Volkswagen ID.3. Let's consider the Infineon IGBT and the inverter stage of Volkswagen ID.3. The Infineon IGBT FS820R08A6P2B is a 6-pack module optimized for hybrid and electric vehicles. This is part of the hybrid pack drive. This implies that the Infineon IGBT FS820R08A6P2B consists of 3 half-bridge IGBTs blocks and a pair of complementary switching devices. Each half-bridge IGBT block is made up of the ID.3 IGBT generation with emitter-controlled diode in the 2247 Plus package, which is an automotive micro-pattern trench field stop cell design optimized for electric drivetrain applications. The ID.3 IGBTs also show excellent light load power losses, which helps to improve system efficiency over a real driving cycle. The ID.3 IGBT was optimized for applications with switching frequencies in the range of 10 kHz. The ID.3 IGBT is an automotive IGBT discrete with a code-packed diode in the 2247 Plus package, with 120 ampere nominal current and collector emitter blocking voltage capability of 750 volts. IGBT is typically a 3-terminal device, namely gate G, collector C, and source S. This is a voltage-controlled device. Unit is located between the rear wheels. The front drive unit, if equipped, is located between the front wheels. The drive units, through their inverter topology, convert the direct current, DC, from the high-voltage battery pack into a 3-phase alternating current, AC, that the drive units use to power the wheels. Tesla Model 3 uses silicon carbide MOSFETs for its central inverter. It consists of 24 silicon carbide MOSFETs from STMicroelectronics with a custom package designed for it. Each of the silicon carbide MOSFETs is rated at 650 volts and 100 amperes. The Tesla Model 3 uses a 3-phase 2-level inverter topology with an input battery voltage of 400 volts. The conventional 3-phase 2-level inverter consists of a DC link voltage and 6 switching power semiconductor devices. As mentioned previously, the conventional 3-phase 2-level inverter consists of a DC link voltage and 6 switching power semiconductor devices. In this case, a conventional 2-level inverter structure with 4 MOSFETs paralleled per switching device to handle the high current. The 4 MOSFETs paralleled per switching device in the inverter is switched on and off by the gate source voltage applied to the gate terminal of the device. Based on the information extracted from the datasheet, the device is entirely switched on when the gate source voltage is within 10 volts to 25 volts. When the 4 MOSFETs paralleled per switching device have the appropriate gate source voltage applied, the voltage across each MOSFET will be 400 volts due to the input battery voltage level of the Tesla Model 3. Furthermore, current flows through the MOSFETs when switched on, while the current stops flowing through the MOSFETs when switched off. Therefore, we have a voltage rise when MOSFET is switched off, and the current falls at that instant with a slight delay. During the turn-on transition of the MOSFET, the current buildup consists of a short delay time followed by the current rise time. After the current flows through the MOSFET, the device's voltage falls to a small on-state value with a voltage fall time. The 2 peak spikes are illustrated to represent the turn-on and turn-off transition. The smaller peak represents the turn-off transition and the energy dissipated in the MOSFET at that instant. On the other hand, the higher peak represents the turn-on transition and the energy dissipated in the MOSFET. The turn-on and turn-off transition is superimposed on the current rise and current fall instance for better illustration. Typically 3-terminal devices, namely, drain D, gate G, and source S. This is a voltage-controlled device. Although we have 4-terminal MOSFET devices now. MOSFETs require the continuous application of a gate source voltage of appropriate magnitude in order to switch on the device, i.e. on state. The gate source voltage applied should be greater than the threshold voltage of the device. The gate current flows into the device when it transitions from its on state, i.e. switched on, to its OFF state, i.e. switched off. This transition occurs when the gate capacitance gets either charged or discharged. In its on state, the drain current follows from the drain terminal to the source terminal. Furthermore, between the drain and source, we have an on-state resistance which contributes to losses during the transition between on-state and OFF state. An actual MOSFET with its 3 terminals is highlighted. The MOSFET is fully switched on, i.e., on state, and approximates a closed switch, i.e., OFF state, when the gate source voltage is below the threshold value of the device. Therefore, the device is operated as a switch. The current voltage characteristics of the MOSFET as a voltage MOSFET device is always packaged as either a module or a discrete device. The module-based MOSFETs is used for high-power applications, while the discrete-based MOSFETs are used in low-power applications. A power MOSFET module consists of 2 MOSFET devices connected in series. Most power MOSFET module is rated at 1200 volts and current rating of about 100 amperes or more. The pinout configuration of the shown power MOSFET module highlights its gate terminals, G1, G2, source terminals, S1, S2, drain terminal, bus. The electrical schematics of the power MOSFET module shows the 2 MOSFETs labeled Q1 and Q2 respectively. Also, the freewheeling diode is attached to both Q1 and Q2 respectively. A discrete-based MOSFET device usually come in either a 2247-3L package, which is a 3-pin device, 3-leg, or a 2247-4L package, which is a 4-pin device, 4-leg. As described previously, the 3-pin discrete-based MOSFET device consists of the gate terminal, drain terminal, and source terminal. On the other hand, the 4-pin discrete-based MOSFET device consists of the drain terminal, power source terminal, driver source terminal, and gate terminal. The operation of either a 3-pin or 4-pin MOSFET can be described using the current voltage characteristics curve, also called the IV characteristics curve. This highlights the operating regions of the MOSFET based on the application of the device. The first region consider is the cutoff region. In this region, the MOSFET have no input gate voltage. Therefore, the drain current is 0 because there will be no current flow through it. The output voltage is equal to the supply voltage. Therefore, the MOSFET is switched OFF in this region. This implies that the MOSFET operates as an open switch. Furthermore, the saturation region occurs when the gate source voltage exceeds the threshold voltage, which allows maximum drain current to flow through the device. Therefore, by applying a suitable gate source voltage to the gate terminal of the device, the resistance of the drain source channel will vary from an off resistance, which is effectively an open circuit, to an on resistance, which makes the device act as a short circuit. The input and gate terminal is connected to the supply voltage. The drain source voltage in its ideal condition is 0 volts in the saturation region. The MOSFET operates as a low resistance closed switch due to the impact of the on-state resistance. The third region is called the ohmic or linear region, where the drain current increases with an increase in the value of drain source voltage. When MOSFETs are made to operate in this region, they can be used as amplifiers. When the input voltage is very high or equal to supply voltage, the MOSFET Q point moves to point A along the load line. The next series of videos, the power electronics technology deployed in the other Volkswagen ID series will be addressed. Remember to push the like button, then the subscribe button, and press the notification bell. Your comments and feedback are greatly valued. Thanks so much for your time and support.